Essentially what we're going to do is we're going to get word stories, and we're going to be asked to find the biggest volume, the smallest perimeter, the fastest speed, the shortest distance, whatever it is. It's going to involve finding a big version of something or the smallest version of something. And when you have questions where you've been asked to find the biggest version and or the smallest version, we tend to group them together into one topic and call them optimization functions. And one of the things about them is that they are not standard. It's not like, well, if I show you one, the next 10 are really just the same question, but with different values. They can be, and very often are, quite different from each other. So these are very, very general strategies. In every story, you're going to find some function, we'll call it the optimization function from the story. And this function has to be, eventually, it has to be in terms of one variable. So let's make sure, just call the variable x all the time. At least we can do that. So I want to find some function. A equals f of x, y equals f of x, any letter you like here. The volume equals f of x, some function in terms of x that we are being asked to find the biggest or smallest value of. We call that function, when we eventually get it, the optimization function. Now, in some questions, you don't even need to find it. They just tell you, which are the easiest ones. But most of them, you have to find it. And some of them, it's not a trivial job. It is quite a lot of work to come up with this guy. And we have to figure out how to do it. That's typically going to be the hardest part of the process, typically. Because once we get that, how do we find the biggest and smallest? We find the derivative and then the critical numbers. And if you find the derivative, that leads to the critical numbers. And one of those critical numbers will be the guy you're looking for. Because critical numbers tend to be the places, right, where maximums and minimums happen, right? And that's what we're after, big and small, max and min. So let's show you a short version of this basic story. So this is find two numbers whose product, let me put a little provision in here, find two positive numbers whose product is, give me a product. What do you want these two numbers to multiply by?
49.
No, that's pretty boring. That's the one in front of me, but we'll do 49. And whose sum is a minimum. Right, so this is actually version question 1. So how am I going to approach this? Well, the first thing I'm going to look at is that you tell me that there's two numbers and the product is 49. So I'm going to call x the first number. I'm going to call y the second number. And I know, because you told me, that their product is 49. And that little guy is going to come in and be very useful later on. Now, the optimization function I'm getting from this line here, whose sum is a minimum. So I'm going to have a function, I'll call it S for sum. And the sum is what you get when you do x plus y. And we're trying to find its minimum. Now, right now, I do have an optimization function. The problem with my optimization function is that it has two variables, x and y, and I need it to have one variable. So this is where this guy comes in. if xy is 49, then does it not make y, if you divide both sides by x, isn't another way of writing that information? Is to realize that y is 49 over x, which means I now have my optimization function. And I've just completed step 1. Find the optimization function. So this function tends to be v equals something, s equals something, p equals something, you know, whatever you've been asked to do. But I have a function now that only contains x, and this is the function that I want to find its minimum value. So step 1, get your optimization. Step 2, let's differentiate this function. Then I'll use this notation. Now, if I'm going to differentiate this function, I have to make sure that, you know, I do it properly. Differentiating x is easy. How do you go about differentiating something that looks easy, but maybe you could make, you know, if you're not careful, could make a mistake? How will I differentiate 49 over x? I have to call it something else, won't I?
Can you do like maybe like 49 x to the power of -1?
You can, and that's exactly what you should do. And if you write it like that, and then you differentiate it, can you just trust me, but you can go in and double check it, that that's what the derivative looks like. So like Cynthia said, call it 49x to -1. Can't you then do the power rule? See if the next time it's a square root of x, won't you call it x to the half and then differentiate it? No. So there's step 2. I have found the derivative of my optimization function. Now, step 3 is find critical numbers. There are 2 kinds of critical numbers in the world. There's the one where the derivative is equal to 0. So I'm going to solve. When is this guy? And there's at least 3 different approaches to this, and they all work. Does anybody want to just jump in and tell me how they're going to solve this equation? It might not be the way I was going to do it, but that doesn't make it wrong. It just makes it different.
Move the 1 over to the 0 by subtracting 1 from both sides.
Okay. Seems reasonable.
And then cross multiply.
Yeah, nothing wrong with it.
Multiply by -1.
Yeah, good idea to get rid of those negatives. Almost there.
Take the square root of both sides.
Which generates 2 answers. Well, let's call them potential answers. X is +7, right? That's one possibility. X is -7 is the second possibility. Why am I kicking out X is -7?
Because it has to be a positive number.
So X equals 7 is a candidate to being the solution, right? But there are 2 kinds of critical numbers, right? The derivative is 0. But isn't there a second kind of critical number? And that's when the derivative is undefined. Is there any value of X here that would be a bad choice, and therefore the derivative would be undefined?
0.
0. Now, let's look at the 2 candidates for the solution to this problem. Our job is to find the minimum sum. Let's take x equals 0. If you plug x equals 0 into here, don't you get 0 plus 49 over 0, which is infinity? Would you agree that that's the exact opposite of what I'm trying to find? You can't get any bigger than infinity, and I'm trying to find small. So I'm kicking that one out for just obvious reasons, right? I'm plugging it in, and I know it ain't the answer. So there's only one guy left, 7.
Why did we cancel the -7?
Can,
Because it says at the top here that we're only
Positive, yes.
asking to find positive 2 numbers. And if it hadn't that restriction, and then -7 would have been also a valid answer, right? A valid possibility. Maybe not the answer at the end, but still a possibility. Now that makes like Sherlock Holmes, right? If when you've eliminated everything else, whatever's left must be the criminal, right? So x equals 7 done the crime, right? There's only one guy left. And let's check it out then.
Can I ask a question real quick?
Yes.
Would the derivative be, why would it be undefined at x equals 0 if it's 1 minus
Put
the
0 in here.
fraction?
Right, what's 49 over 0 going to get you?
An undefined, but what happens to the 1?
Well, it's a bit like it doesn't matter. One take away something's undefined is still undefined.
Oh, okay.
Right.
Thank
Like
you.
one takeaway one takeaway in infinity is still infinite. The one's not going to help it any. Right, so we have x equals 7. That's cool. So what's the other guy? Well, y is 49 divided by x, which is 49 divided by 7, which is also 7. So it looks like find 2 numbers whose product is 49, whose sum is a minimum. The 2 numbers are 7 and 7. And the sum that they get is 14. So we've solved our first puzzle.
When you said y equals 49 over x minus 49 over x, is
No,
it supposed to be
it's
y equals
49.
1?
It's equals
Oh,
minus, it's an equals, just a very faint equals.
I see. All right. Thank you.
So fraction, replace as.
I thought we were going to put, oh, I see.
Kind of getting crunched in at bottom for space. Now, I won't do the next question, but we'll set it up. Question says, find 2 numbers whose difference is 62 and whose product is a minimum. It's a bit like switching the story around. Right, so what do I know? I'm going to call x my first number. I'm going to do y, I'll call that my second number. I know the difference is 67. 62, I should say. And the optimization function is whose product is a minimum. So I'll call it P for product, X, Y. So this is the optimization function. Now, right now, this function has X and Y in it. How am I going to get this to just be in terms of X?
divide y from both sides.
I'm not sure where your thoughts coming from.
You gotta solve the y, I mean, x minus y equals 62 for x, yeah.
Right. Is that what you were meaning then? If that's
Yep.
the case, I agree with you, right?
Yeah,
So,
y equals,
so if I add y to both sides, then I take away 62 from both sides, I get this guy. So that guy led me to this. And so I now have this one. And now at this point, you can differentiate, find critical numbers, and you'll get your answer. But in this question, I just got you to the optimization function. Question 3.
can you explain a little bit about,
Yes.
why, I mean, I can see myself confusing and making the, x minus 62 equals y the optimization function. So how do I know?
But
which
that's
one?
not in the story. There's a piece of the puzzle that says that. Find the product that is a minimal. X minus 62 equals y is not a product. You're not going to optimize that.
But it
You're
also
going to
says whose
optimize.
difference is 62. What if I?
Yeah, but that's a given piece of information. It doesn't say whose difference is 62 and minimize the difference.
Okay.
It doesn't say minimize or maximize the difference.
Oh,
It does
I
say
get it.
minimize or maximize the product. So the
I get
thing
it.
that you're being asked to minimize or maximize is going to be your optimization function. The other piece of information, if they give you it, is, as it is here, is it going to allow you to convert this function into just a vexes. Third one. What is the maximum vertical distance between a straight line, y equals x plus 30, and the parabola, y equals x squared, but you're only going to be using x's in that range. Can you imagine this is y equals x squared? And can you imagine this is y equals x plus 30? If you take a random point here, that's the distance that they're calling the vertical distance, right? And you're only doing it from, whatever, I don't know where -5 is, from -5 to 6, right? So you're only interested in it in that range. And it's the maximum vertical distance between them. So we need an optimization function I'm going to call D for distance. What would be the vertical distance between those two? In terms of x, what would the vertical distance between the straight line and the parabola be?
I guess x plus 30 squared.
I think a little bit different than that.
X plus 30 minus x squared.
That sounds like a difference between two things. The difference between this guy and that guy could be x plus 30. Take your x squared. Isn't x plus 30 the straight line? Isn't x squared the curve? Isn't the difference between those two the difference between the y value of the straight line and the y value of the curve? X plus 30, take x squared. So there's the optimization function. Now, not the hardest thing in the world to differentiate. Agreed? I'm assuming that there'll be just one critical number. And that critical number, hopefully, is between -5 and 6. And if it is, you're done. Yeah. Question 4. Find the dimensions of a rectangle. So find the dimensions of a rectangle. With a perimeter of 76, whose area is as large as possible. So I'll draw a little rectangle. And I don't know what the rectangle is, so I'm going to call this distance X. I'm going to call this distance Y. So the length is X and the width is Y. Based on this story, what are we trying to optimize? What is it that we're trying to optimize? Are we trying to optimize the length and the width, or the area, or the perimeter, or what are we trying to optimize in this story?
The area?
Right. The area is as large as possible. So area of a rectangle, at least the way I've described it, is into X times Y. Now it's very similar to the two numbers add up to 7 kind of question, right? We have X, Y. What else do I know? There's only one other thing in this story that I am told. And I am told that the perimeter is 76. Right, the perimeter of this thing is 76. Now the perimeter is 2x plus 2y, and I'm told it's 76. Can you see that that piece of information that I've just written down is going to allow me to figure out who y is in terms of x? Right? The perimeter equaling 76 is going to allow me to take this y and write it down in terms of x. So what I'm going to do is I'm going to subtract 2x from both sides and then divide everybody by 2. And I get that, which means that we now have our optimization function. The guy we are trying to, in this case, maximize. Are we happy about how we created the optimization function and got it at the end, at least, to only have x's in it? So that's essentially my step 1. Okay, what am I going to do next?
Derive it.
Okay. And if you differentiate it with respect to x, you get 38 take away 2x. I mean, the derivative part of these, so far anyway, hasn't the derivative part been one of the easiest things? We haven't really had really strange functions. Okay. Don't I now just find critical numbers and I hopefully should be finished? Step 3 coming up. I need to find when the derivative is 0. Well, there is the derivative. Yes, if you add x's to both sides, you get the answer 19. That's actually the only candidate in town, isn't it? There isn't any other choices. So that means the length of this rectangle is 19 meters, right? That's what X was. And the width of this rectangle is whatever that is. And what an interesting Doesn't this rectangle end up being a square? And then if you think about it, it kind of makes sense. Wouldn't the most efficient straight-edged shape, right, the most efficient rectangle, wouldn't it be a square? Kind of makes sense. And that's this question done. Are we okay with that one? Are you beginning to see, although there's a lot more variations still to come, are you beginning to see the thought process involved in having an optimization function, right? Something with x's. Because once you get that, you've kind of broken the back of the question, haven't you? Because then calculus takes over and it finds the critical numbers. And you know one of those critical numbers typically is going to be the guy you're looking for. And if there is only one number, then your life becomes really easy, because that is the only answer.
I was thinking that we would have plugged that x equals 19 into the original equation that was y equals x plus 30.
Y equals x plus 30.
Yeah,
Where
the
is
original
x?
one.
Where is x plus 30? I'm looking for it.
Oh, okay, forget it. I guess I'm mixing up two different problems.
You are. Yes.
Sorry.
I can see it now. I can see an x plus 30 in question 3. Yeah. Not that I've ever done that. I've never made a mistake. Now, the next bunch of questions, questions 5 and 6. Yeah. You are given the optimization function. So step 1 really doesn't matter. So what's the problem? Well, let's show you the problem. The yield that you get from a crop is given by the formula Kn over 49 plus n squared. And n is the variable. And k is a constant. And basically, n is how much nitrogen you put into the soil, and y is the crop yield, right? So if you put in 5 units of nitrogen, you get 10 ton of weight. Put in 8, units of nitrogen into the soil, you get 50, and so on and so forth. And there's a magic number that we're looking for. We are being asked to find the nitrogen level that maximizes y. But that's not how they phrased it. They phrased it as find the nitrogen level that maximizes the yield. So we had to, basically, it wasn't much of a translation, but hadn't we to figure out that find the n that maximizes the y. Right. Now, if they hadn't even seen that, if I looked at this, I know what I'm going to do. Aren't I going to differentiate this guy and find critical numbers, because that's where max and mins always live, right? So I'll write the guy down again. And I'm going to differentiate him and then find his critical numbers. Now this guy is a quotient rule. Agreed? Not the worst function on. I think the only awkwardness about this isn't it the k. But remember, k is a constant, so just think of it as 42 because it's just a number. So it's going to be f dash g, take away f of g dashed, all over, oops, almost put the thing in there, all over g squared. Okay, let's start with the top. What do you get if you differentiate kn with respect to n? What's the derivative of kn with respect to n?
Just n.
K.
Yeah. 42n gets you 42. Right?
Ah,
17n gets you 17. Kn gets you k. You see, some days a variable, some days the constant. Multiplied by the untouched bottom. Take away the untouched top, and if you differentiate this guy, you get 2n. And the whole thing squared. Distribute the top, I get 49k plus kn squared. Take away 2k n squared all over. Okay. I get 49k, take away a k n squared over this guy. Okay, is there any style points you can do to the top? (49k) take away k n squared. Is there anything you can do there?
You can take out a k and then factor it.
Okay. I like your thinking. And do you recognize, I'm sure you do, that it's a difference of two squares? So we got this guy, right? Looking good? Right, so now that I have done as much as I can with the derivative, I just rewrite it up here. Let's find the critical numbers. Because one of these guys, one of these critical numbers, is going to be the one that maximizes the yield. Step 3. Find the critical numbers. Well, the most obvious ones to look for are the ones that make the derivative 0. Now, because I've already written this in a nice factored form, it should be pretty easy to find the values of n that make this derivative 0. The ones that make this derivative 0 are the ones that make the top 0. And the values of n that make the top 0 are -7 and the other one 7. I'm going to throw out that as a possible answer. Why am I not going to make -7 a number that is a possible solution? Why am I kicking it out?
Because you can't have -7 nitrogen.
Right, so it's in the context of the story, right? If this was a story about temperatures, wouldn't I keep -7 in because that could be a temperature, right? If it was a story about apples, I would throw it out because you can't get -7 pound apples, right? You know, context of the story sometimes can eliminate a choice. Is there any value of n for which this derivative is 0? Well, for that to happen, doesn't the, this derivative to be undefined. For that to happen, doesn't the bottom have to be 0? Would you agree that 49 plus n squared is always positive, so it's never going to be 0? So I only have one answer. That makes life easy. If there's only one answer, it must be the answer. So what do I know? I know that if you have a nitrogen level of 7 units, whatever 7 units of hydrogen looks like, then you will have the maximum yield. And if they wanted to know what that yield was, I'd return to the original formula. And I tell you, it's whatever K over 14 was, if they asked for it. How are we doing? Is the process behind this begin to make kind of sense on how you approach each puzzle, right? You take on its mirrors. This one here, right, the one we're just finishing, was quite different from the two numbers add up to 49 and maximize the product, right? That kind of thing, right? But it's still an optimization function. The goal is to get an optimization function, right? And if they tell you, your life is a lot easier. But in many cases, you have to find it. So that brings me to question 7. Okay. Too much to just read it to you. Let's show you. Right, hopefully you're looking at question 7. Can you see it on the screen? Am I sharing it?
Yeah, you're
Okay.
sharing it.
Right, here it goes. Consider the following problem. So I'm writing this down in my paper as I go through it. Consider the following problem. A farmer with 700 feet of fencing. So total fencing is 750 feet. I wonder what he's going to do with this fencing. He wants to enclose a rectangular area and then divide it into 4 pens with fencing parallel to one side of the rectangle. Right, so I'm drawing a rectangle right now. And he wants to break it into 4 pens. Well, you can't see me doing it. I've just drawn 4 vertical lines. So I've got 4 little baby rectangles inside the big one. And what is the largest possible total area? So I'm writing that down. What's the largest total area? And in that question, they actually kind of take you through the same types of steps I'm about to do. So I'm not going to call them A, B, C, and D. You can figure that out later. But that's the gist of what's going on. Now you might think, well, why did you go vertical? Could you have went horizontal? Yes, I could. Would it change the answer? No, actually, you end up with the same result. So, because isn't that guy also that guy? Agreed? You know, just orientation, right? That guy is that guy, right? So I know the total amount of fencing is 750. To maximize the area. So the area function, well, I'm going to have to label some things. So I'm going to call the length X. I did that the last time. So I'm going to call this distance here X. And I'm going to call the width Y.
Was the total 750 area or was the total 750 the length of the fence? Because I thought it was
It was
just,
the length of the fence.
okay.
If it was the area, then the question would have been over with because the answer would have been 750. Oops, then this guy is 1. Now, the optimization function is the area, which is x times y. Actually, we've done a rectangle question before and it was x times y. Over here, I'm going to use the fact that the total amount of fencing, right, using the outside and these inside pins, came to 750. So you would do 2 pieces worth x and 1, 2, 3, 4, 5 pieces worth y, and that's 750. Are you happy about 2 x's and 1, 2, 3, 4, 5 y's? Even although there's only 4 guys, which is what you wanted, have you noticed that you need 5 y's to make that up? Now that guy, if you subtract 2x on both sides, and then you divide everybody by 5, you get 150, take away 2/5 x. You have the A is x times 150, take away 2/5 x. So the optimization function ends up being a really relatively simple quadratic. And that's step 1 done. And I think that's question A, B, and C, according to them, right? So by the time you get to C, you'll have this. And can you imagine where this is going to go? Because I'm not going to finish it. Right? Aren't I going to differentiate that guy, find a critical number? There's probably only going to be one, and that's going to be the size that x is. So that's how long the fence is going to be. And then we calculate y using this guy, and that's how wide this rectangular field is going to be. And we're done. Now, the next one is question 8. I'll just read this out. Consider the following problem. A box with an open top is to be constructed from a square piece of cardboard 3 feet wide by cutting out a square from each of the 4 corners and bending up the sides. Find the largest volume that such a box can be. Wow. So here goes. I have a square piece of cardboard. It's 3 feet by 3 feet. I'm going to cut out some corners. And these corners in the story that they just gave me, I'm going to call x's. Because they have to be squares, little square corners. Now, if you imagine cutting them out, if you then bend the pieces, I don't know, maybe shade them, right? If you cut these guys out, can you see that if you bend up what's left, won't you be left with an open topped box? Actually, that does look like an open top box. I'm getting better at being an artist. It took 60 bloody years. That's a box. It actually kind of looks like what I was hoping it would look like. Now, what we've been asked to do with this box, we want this box to have the largest volume. So somehow or other, I have got to figure out what the volume of this box is in terms of x, because won't that be the optimization function that we're after, right? Right. The volume of this box, right? Try to find its largest volume. So the volume of this box. Now, if I call this box length, width, and height. Let's see what I know about this box. Length, width. This distance here, I'm going to call that the length. What is this distance here in terms of x? Well, I know that from there to there is 3. But don't I cut an x off this side and an x off this side? So what does that make this length?
3 minus 2x.
Great. Now, if we call this side here the width, isn't this distance 3? But the guy that's my little L, the guy that's this distance here, won't that be my width? And what's the width going to be in terms of x?
The same.
Now, before you say, 3 minus 2x, don't. When you bend the little flaps up, what is the height of this box going to be? It's not going to be 3 minus 2x.
X.
It's going to be x. Are you happy about how we constructed the values for length, width, and height with x's in them? So I want the largest volume. So isn't the volume the length times the width times the height? Isn't the volume going to be 3 take away 2x, 3 take away 2x times x? Now if I FOIL this guy out, you get 9 take away 12x plus 4x squared times an x. You get 9x take away 12x squared plus 4x cubed. We've finally got step 1. My optimization function is a cubic, isn't it, in this case? Now, can you imagine step 2, differentiate, find out its critical numbers? I've got a feeling there are going to be 2 critical numbers here. So how do I know which one's the right one? If you can't kick one of them out because it's, say, x is -10, right? So if you got x is -10 and x is +2, don't you just keep the +2, right? But if you can't kick it out, if one of them says x is 4 and the other says x is 6, just for argument's sake, right? Wouldn't you just basically plug both numbers in, and whichever one was the biggest volume, that's the right answer, and you'd be good that way? They're kind of fun, these, aren't they? They get a little challenge to them, a little twist. Or I think they're kind of fun.